When performing tasks, autonomous robots must make energy-aware decisions to operate effectively. For example, consider drones delivering parcels to customers. They must constantly monitor their remaining charge and return if it drops to a critical level. This can result in wasted energy, delayed deliveries, and even safety risks, such as a drone crashing. Our work focuses on enabling robots to make smarter, energy-aware decisions. Before starting a task, a robot evaluates its available charge and determines whether it's sufficient, asking itself, "Can I deliver this box to the required location with my current charge?" While this approach helps avoid earlier issues, implementing it on robots is challenging. Energy consumption models are often uncertain and can change over time. The challenge increases with groups of robots, as each has a unique energy profile influenced by manufacturing differences and varying usage. We consider an on-demand UAV-based delivery scenario, where a fulfillment center operates a fleet of UAVs to handle orders that arrive stochastically. Each order has an associated parcel mass and delivery distance. Given the parcel's mass, delivery distance, and a set of UAVs with varying charge levels, the problem is to determine whether any UAV can deliver the parcel, and if multiple are available, which one to choose. These decisions must be made without knowing the exact energy models and the heterogeneous conditions of the UAVs. To address this problem, we propose a method that combines auction-based task allocation with online learning. Our method is implemented through 3 interconnected elements: the UAV's core controller, auction policies, and an online learning element to update the bidding policies. For each delivery task, UAVs submit a bid if they believe they can complete the task with their current charge and attempt to deliver if it wins the auction. It returns to the fulfillment center either after successfully delivering the parcel or aborting the delivery due to insufficient charge. Each UAV decides whether to bid or not using its bidding policy, and if it does, it bids a value that reflects its confidence in completing the delivery. Regardless of the outcome, this experience is used to adjust its bidding policy, enabling the UAV to better understand its true capabilities. As a result, UAVs learn to bid only on tasks they can complete. We developed a multi-agent simulator to evaluate the performance of various bidding strategies in long-term deployment scenarios. First, we examined how the rule for determining the auction winner affected the delivery performance. We compared 3 approaches. The least confident, the most confident, and a random UAV was chosen as the auction winner. Counterintuitively, the least confident rule outperformed the other 2, consistently delivering more parcels in less time. This was because using the least confident rule allowed the UAVs to achieve better learning. The UAVs were more likely to be awarded tasks near their capability limits, leading to a more valuable learning experience. Also, selecting the least confident rule achieved smarter resource allocation of UAVs. This heat map shows the battery health of the winning UAV when using the least confident rule, assuming all UAVs are fully charged. As the charge level decreases, the more capable UAVs take on the more challenging tasks. This strategy ensures tasks are assigned to UAVs with the appropriate level of capability, neither uncapable nor overcapable. This preserves more capable UAVs to more challenging tasks. Next, we compared our approach to a traditional threshold-based strategy, where UAVs are deployed only when their charge exceeds a predefined threshold. Our approach consistently outperformed the threshold-based strategy by allowing UAVs to bid and deploy at any charge level, provided they predicted the task achievable. We also explored a variant of our approach, where UAVs with insufficient charge could bid for a parcel and deliver it later, once they had accumulated enough charge. This forecasting mechanism enabled UAVs to prioritize older parcels, ensuring they were delivered more promptly. In summary, we proposed a decentralized learning-based deployment strategy for UAVs with unknown energy consumption models and varying battery health. We conducted a long-term evaluation of our approach over 8 weeks, using a fleet of simulated UAVs. In addition, we proposed a variant where UAVs leverage their learned bidding policies to forecast and commit to delivery tasks at specific times in the future.